Hey guys, and welcome back to class again. So we've been going through a series on charges and electricity, and we finished up the last video with a discussion about what current is. And current is nothing but it's a rate of flow of charge in a circuit. So if you remember, every electron has a charge. So one of the easiest ways to look at a wire is essentially look at a wire like it's a pipe. That's a good way to understand it. And so in that pipe, you have electrons that are moving. Each of those electrons has a charge. If you remember, 1.6 times 10 to the negative 19 coulombs. So current, say for example, you had 1 amp of current flowing through a wire. What does that tell you? Well, remember, what current means, it's charge over time. So that tells you that there's 1 coulomb of charge flowing for every second through that wire. And that is the easiest definition what current is. Now, that brings us to today's topic because there is 1 and 2 types of current. Now, as a child, I can remember being brought up in through the 80s, the band AC/DC in particular. Hit the sack. Never mind, I won't do that again, and I apologize greatly for it. But I remember everybody always talking about AC/DC and what it meant, and people would say Antichrist, Devil's Child. Actually, the logo literally meant AC/DC, alternating current, direct current. Their mother was a seamstress, and on the back of her sewing machine was a logo. They thought it looked cool, and they went with it, and thus AC/DC, alternating current, direct current. So I guess best way to actually look at this concept of AC current DC is actually just build a circuit. So let's grab a battery. And this is a FET that you can play with through the University of Colorado. And I love all this stuff that they have. And I encourage you, any of these FETs that I use, you can see the titles up in the corner. Go and play with these yourself. I'm going to get a light bulb now and put in here. If we were in school like normal, that is exactly what I would have you doing right now. And now what's funny is there's a challenge can be made. Could you make a complete circuit with only 1 wire and 1 bulb? And yeah, there's actually 4 different ways to do that if you have a flexible wire. Unfortunately, this wire isn't flexible, so that makes it rather hard for me to actually do that. But anyway, it's kind of a neat little trick to see if you can figure out how to wire a bulb up. Because remember, with the bulb, it's got to complete a circuit. So like right now, I don't have a complete circuit. I've got to connect the other base of the bulb has got to be connected to the other end of the battery. So for me, I'm going to grab another wire and then grab 1 more wire since these wires aren't bendable. And now I've got a complete circuit. So let's play the simulation. And now you see the light bulb light up. And the big thing is I want you to notice are these electrons moving through the wire. And if I increase the voltage, you could probably expect to see more electrons. But you see the electrons are moving one single direction. They're coming out of the battery and they're eventually returning to the other end of the battery. Now, this is DC electricity. So if you've got a 1.5 volt AA, AAA, DC battery, 9 volt, whatever you got, it's going to be working the flow like this in the circuit. So now I want to do something. Let's get rid of that battery. And let's do this. Let's grab a hold of an AC power supply and put in. An AC source would be like your wall outlet. Oh, except for me, I'm making a huge mess of my circuit. And all I know to do is try and free. Wow, what happens? Don't cross the streams. Wow, I don't think I could have made much bigger of a mess than this, could I? Let's try this one more time. So let's get an AC power source in. I want to turn it sideways. And now let's connect the AC source and hit play again. Now look carefully at the electrons. The bulb is still lighting, but if you notice with an AC source, all it's doing is it's moving the electrons back and forth. There's something known in physics as drift velocity, which is basically how fast is the electron moving in the wire. And I once asked a question about a light shed or a shed behind somebody's house. And it was a trick question because I asked, how long would it take, like seconds, for the electron to reach the light behind their house? Well, it was a trick question because with AC electricity, like this electron here, I've got my finger on it. That electron's never going to reach the light because in AC electricity, all they do is oscillate. Now, we see this bulb growing bright and dim and bright and dim. In real life, we don't notice that effect in our light bulbs because our electricity in our homes is vibrating at 60 times a second. And I think if you travel overseas, it goes to like 50 hertz, something of that nature, which is why your USA appliance may or may not work when plugged into an outlet in the European Union, for instance. But anyway, we got a little basics there on this AC-DC. If you take a look at my notes, you see this 60 hertz here, generally for US. And this actually goes all the way back. If you want to see something interesting, go read up on like Tesla and Edison. Edison was a huge direct current guy, and Tesla was the alternating current guy. And obviously we can see who eventually won this little battle. But the big difference is AC electricity, it's easier for transmitting electricity over long distances. And so eventually that won out. This DC electricity thing, it's only good for localized use. Now what's funny is I've threw it in the notes. Most electronics actually use DC electricity. So what you do is you have a device known as a rectifier, and that rectifier essentially converts your AC electricity back to DC electricity for your device to use. So anyway, a couple other terms, and this is going to be a short video at that point. Potential difference, you're going to hear me use the word potential a lot. People are always saying, like, when you look at a battery, like look at a AA battery, they'll say, well, that's a 9-volt battery. That's a 1.5-volt battery. They're referring to the potential of the battery. The easiest way to talk about potential is essentially potential to me. I think of it like, this is me just going off trying to make it easy to understand. But I think about potential difference as the ability of something to literally push the electrons. So let's say you had a battery with 1.5 volts of potential. And here I'll put like two little plates up here. And so you try and push this electron. And so you have 1.5 volts of potential. So obviously the more volts you have, the easier it is to actually push and give energy to this electron, because that's what it comes down to. It comes down to this ability of energy. Matter of fact, if we were in straight physics right now, I would write something like this. Potential energy is equal to a charge, because it depends on the charge you have, and the product of the potential, the change in potential, and the charge tells you the potential energy. And what's cool is that potential energy, then, let's like go back to this earlier example I drew up here. You can literally take an electron and push an electron, and you got to think, that means you can actually convert that potential energy to kinetic energy. Old AP physics exams used to love setting up problems based on this. They would use this: charge times volts equals 1/2 mass times velocity squared. It made for a really neat little problem. Q was the charge of the electron, and M was your mass of the electron. And if you knew the potential, like say you had 2,000 volts of potential, you could calculate the speed that velocity would be going. Now, this is like in free space, not in a wire. In a wire, you have to take into account the conductivity of the wire. But anyway, as we go through and we kind of finish this up, one of the other cool things about like batteries is your ability to stack batteries together. And so like you notice in most appliances, they use like multiple batteries. Like my TV remote uses 4 AAA batteries. And most people don't know this. They think there's a difference. AAA, AA. Actually, it's kind of funny. The pin to this Microsoft Surface I'm using a quadruple A. I did not know a quadruple A battery existed before buying this Surface. But a C battery, a D battery, they're actually all 1.5 volts. So the whole difference in size of the battery really talks about the length of time they can continue to supply that 1.5 volts. But again, like your remote control, if it uses 4 AAA batteries stacked, then you've actually got 6 volts of total electricity in there. So let me check the time on this video. It's 10 minutes, and we'll probably shut it off. What we want to look at next is actually like with power. Let's do this. Let's just do a basic power problem first. Now, we know that power, go back to like older units, is work divided by time. Or if you want to be really cool and like physicsy about it, you could do like the derivative of work with respect to time. You could also just say, though, power is basically energy over time, is another way I like to look at it. So kinetic energy, potential energy, there's all kinds of ways we can do this. And now that if we think about it in terms of potential energy and voltage and things of this nature, look at this. We just learned a second ago that potential energy is charge. Potential energy is QV. Now put that over time and look at what you get. Charge over time, that's current. So that means, and here's the equation already written out, power is equal to current times voltage. So, real simple question, we'll finish the video up. Just ask, if you have a 12 amp vacuum cleaner plugged in a 120 volt outlet, how much power would you be using? Well, power is equal to current times volts. So that would be equal to 12 amps, and I just wrote volts, 12 amps times 120 volts, which in that case would be 144 or 1,440, and the unit is still watt, because watts are the unit for power. So anyway, it's kind of neat getting to derive where this equation for power comes from. Anyway, those are simple problems if you get thrown one of those. So anyway, thanks for watching. We'll catch you later.